introduce to you a little bit of what we are doing when it comes to power systems and digital twins here in the Netherlands. I wish that we have, let's say, results already, but we are just starting with this, developing this technology, and we have really good news in terms of the efforts that we are doing in the country together with also the transmission system operator, TenneT. And we want to share what are our ambitions when it comes to power system digital twins in the country. And of course, open to share and hear feedback from what we are doing. So a little bit of context, the context of what we are going to discuss. I will go very quickly about who we are, what we do here at TU Delft in the Netherlands. And then I will dive into a very interesting discussion. What's the difference between what we know as a digital twin and what we understand for simulation models? I think that it is important to make this differentiation when it comes to talking about digital twins. Then we will present some of the, let's say, concepts that we are developing here, thinking towards these advanced architectures and models for this vision of power system digital twins, and some of the concepts that we are already researching and let's say imagining when it comes to these architectures, power system digital twins architectures. We'll discuss more in detail, and a little bit of a national program that I'm also leading, and we are kick-starting, let's say, which we call Twin NL. So yes, a little bit about myself. As you mentioned, Rajendra, I'm an associate professor at TU Delft, Technical University in the Netherlands, working on the intersection between digital technologies and, in general, distribution systems. One of those digital technologies is what we call as digital twins, but I also work with AI, for example. I'm part of a broader, let's say, research group that focus on so classical power system from different perspectives, from the classical power systems operation to integrated energy system, of course, reliability and resilience, but also from the flexibility, right? Which is very important when it comes to the future of this infrastructure. So very short about myself, and then let's go dive into the content of the presentation. So digital twin versus models. What's the difference between a digital twin and what we know and what we learn, let's say, in our education of what it is a simulation model? So a little bit of brief of history. I believe that you are aware that digital twin as a concept. They were originally introduced by NASA in 2010, and the definition was very, let's say, precise, right? An integrated multi-physics, multi-scale probabilistic simulation of as-built vehicle. In this case, was customized to one particular application with one particular objective, which was to mirror the life of its corresponding, let's say, flying twin. So when the concept of digital twin was developed for thinking of operations. So having a digital model of a physical system or entity that it was capable of let's say, reflecting in real time. So the word that the NASA used on their simulation was mirroring of real time the operation of the physical system. Of course, the concept was developed for vehicle monitoring at that time, but has departed from there. And I think that we have spent a lot of time now thinking how, for example, this concept could also be used for power system, right? And that's what we do in this task force. And let's say the initial focus was how can we use it to solve technical problems in this particular application for space vehicles that were not physically located here in Earth, right? That was the initial application for NASA. In short, the initial application was focused on real-time operation, and most of the digital twin, let's say, focus on this particular application. Several points when it comes to this with the NASA definition of digital twin. First, it doesn't clarify the role of the model itself, right, in the digital twin concept, let's say, which as a result leads to some, let's say, misconception. What's the difference then between what it is here as an integrated multi-physics, multi-time scale probabilistic model and the digital twin itself? If this concept is not clear, then any model that is available could be considered as a digital twin, right? And that's how this misconception is leading to some people thinking that they are indeed using models that they just can be replaced by digital twins, or the models that they are using can be called as a digital twin. So just to give you a glance of why this discussion is important, this word cloud that you see over here that we also had in the report from the task force, just highlight how important the word model is within the concept of a digital twin. So this word cloud is composed using many different definitions of what a digital twin is for many different applications. So not only power systems, and then you see the ones that are more, let's say, significant for the definition itself. We see the model, we see the physical, we see an object, right? It could be a system, a product, and we see virtual, so a virtual representation. So what we see is that in general, there is indeed a connection between a physical model or system, which in this case is the object, and a model, and a virtual representation. The question then, and this is important, what it is missing in this definition is what about lifespan, right? How the digital twin can be integrated also not only for operation, but also for the remaining lifespan of whatever infrastructure that we are modeling with digital twins. And if we are thinking of the electricity infrastructure power system in particular, then the question, of course, is what is the lifespan of the power system or of the electricity infrastructure? So in general, the agreement exists, and we recognize the link between the physical and the virtual system via some models. But the difference between the model itself and the digital twin is not precisely in the definition. So just to give you a little bit of context, the way that we teach our students in our courses on power system digital twins about the difference between these two concepts. And of course, you are freely welcome to challenge what we do. We always like it because we learn more. So we have in general the world, the real or imagined, could be virtual, it could be a system, right? In general, what we understand as a model of any system or component is just a simple representation of a particular domain or reality. The model only represents a particular domain of a whole system or component of a system. So if we want to model that particular world or component, we usually use equations, right? That's what we know as a model structure. There are different ways of models, and this equation, of course, they have some parameters. This is what we call, let's say, in modeling engineering as parameterized model, right? And of course, there are other concepts that are very important. So we have, for example, algorithms, which is sort of the steps that we use to evaluate the model. We have also what is called as a simulator, which is basically the codes that runs the algorithm on a computer, or the algorithm that runs the way that we solve our model. And of course, this is necessary depending on the complexity itself of the model structure that we have, right? And of course, after solving this model with certain parameters, then we get some models or simulation results, which usually these are numbers. So this is in general what we call as a simulation. So we try to do, we simulate a real world system via a model, right? And there is this connection between the model itself, because there is no exchange of information between the model and the real world or component. Now, when we think of a digital twin, we think of making use of a model and connecting such advanced models to the real system via measurements, right? So there is an exchange of information between a model and the real system, and that's what we call the sort of digital twin, the first application of digital twin, in which when we mirror the operation of this world that we are modeling. And of course, the digital twin should also be able to, in fact, apply some control, right, in the system, in the physical system itself. So what you see over here is that the model is a part of the digital twin, but it's not the digital twin itself. What are the pieces that are missing? This is what I'm also going to discuss when it comes to all the, let's say, IT, ICT functionalities that are missing in order to enable these simulation models to actually being capable of processing information, capable of processing measurements, how these measurements are used to fit the model, right? And how they can be used to make decisions to later then use these decisions to be implemented or to add upon the world via some control infrastructure. So the idea is that at the end, this digital twin sort of via this model that is only one part of it represents a digital copy of the world. Now we go to this discuss then the other, let's say, models, components, functionalities that are missing beside these simulation models that represent the physical system. Before going there, I want to discuss some of these key features of digital twins, for particular, the power system. So when we think of digital twins for power system, we also think of going beyond just this physical digital connection. We think about processing data, and that requires, of course, services and models that are developed and they deploy functionalities that are for specific applications. For example, you can think of processing, visualization, interfaces of data, simulation models. We discussed that already. Decision-making models. So all these services and models that provide support to more advanced functionalities. And we also think of planning, right? I presented before the question of how can we also make digital twins, how can we make use of digital twins not only for real-time operation, but also for planning. And how can we use it, for example, to guide the design phase of the infrastructure, in general, guiding the planning decisions. So what we see in the figure here is that we are trying to put all these different features of a digital twin together and try to expand the definition of the digital twin to go beyond just mirroring the operation of a system, and also being able to use it for planning, right? For how the infrastructure evolve with time. So what I'm going to present next is an architecture that we developed together for power systems and digital twins. And this architecture was developed and together with the distribution system operator here of Amsterdam, here in the Netherlands, in which we are actually trying to put together a sort of framework in which we could think of digital twins not only for real-time operation and control, but also for planning. So the proposal that we had here, let's say this is a result of a hard, let's say, of a work of co-creation together with the operators, the way that they see this digital twin, let's say, technologies and how it could be useful for them. However, this is not fully implemented. We didn't have the capabilities to fully implement it in the project that we were together. We did implement and test some of the functionalities, but not the whole architecture as well presented here. The first, let's say, important result is that we reached that the digital twin in general as an implementation we see the digital twin development and implementation as a comprehensive software ecosystem development. So which means that we can borrow concepts from software development. So we can think of standard models, architecture, data exchange, protocols, APIs. And by doing so, then we can start recognizing which of these, let's say, standards, protocols, APIs are already available to reuse everything that is already available, and how can we organize this knowledge in terms of what we think of how a digital twin should look like. In general, we designed this architecture to be a standard architecture in a way that can facilitate deployment of new functionalities and features, but also integration with already available DSOs and TSOs tools and models, but also define a clear orchestration between all these different digital twin modules. And of course, a digital twin is fed with data, lots of data. So we also need to deploy these, let's say, capabilities of data collection, storage, sharing, and visualization capabilities for visualizing data. So I'm not going to go in detail on all the different models that we have here in the architecture, but I want to present to you in high level how this standard architecture, our proposal for a standard architecture look like. So first we have the physical, the differentiation between the physical layer or the physical world and the digital world. And of course, we have here all the measurement infrastructure from power systems, right? You can think of measurement units. You can also think of smart meters at from the customer side, measurements at the generation. So all infrastructure that is generating data. And we have, of course, the connection with the DSOs and the TSOs operational centers. So something important here from the discussions that we learned working with the Dutch TSOs and the DSOs is that they don't see digital twins as a possibility of replacing their tools, right? But rather into technology that could be used to enhance, especially the integration of the different tools that they already have. Of course, that's a vision more in the short term. If this technology reaches the maturity level that we are aiming for, why not? Why the expectation is not for these technologies to replace the tools, for example, that the operators are using right now, especially when they promise coordination and exchange of information between models and tools that are actually right now operated, let's say, in an independent way, in a separated way. So the architecture that we presented here is has a clear boundary, and it comprises, let's say, is a modular architecture which enables interoperability, scalability, some standard interfaces, and it has some specialized components that I will go over them very quickly. Once again, we have not identified all the standard interfaces, all the APIs, all the protocols that are needed, and this is what we are working on right now. So in general, we distinguish 4 components. The first one collects all the planning and operation models, right? And this could be, for example, the planning and operation models. These are all the sort of processes that the operators use. You can think of control, dispatch, observability, stability, long-term maintenance, investment planning. So this is what it is presented, for example, here in all these different blocks here. So these are the operation and planning processes that they relied on models. And this is the second main components of the digital twin, which is clearly separated from the other one, in which we have a collection of high fidelity simulation models. So we can think of multiple models. And for that, of course, we need a management. Depending on the type of operation and planning model, you will have available a different type of models, depending on the time scale that you would like to simulate, depending on the type of physical phenomena that you would like to also to simulate. And 2 other models that are more, let's say, engineering from the engineering side. So we have data engineering and data analytics models that are capable of managing large amounts of data with different spatial temporal resolutions, formats, and quantities. And because we are thinking, for example, of managing data from the infrastructure itself, this is easy to already identify a standard that is available. And here in Europe, the CGMES, the Common Grid Model Exchange Specification, is the one already moving forward as the standard for defining, for example, let's say as the semantic being used to describe the electricity infrastructure by the TSO, the transmission system operators, but it's also being tested by the distribution system operator. And then finally, we have the sort of analytics, which is in general data analytics of all the data being available. So the question is, what's next? What comes after identifying this, let's say, this architecture? So we have a standard architecture because we do research, of course, we want to focus on the modeling side. And there are some questions that, from the modeling perspective, the TSO has already asked to us here at TU Delft. First, how do we organize energy sector modeling data, right? CGMES is one of a possible solution for organizing infrastructure data, but there are still other type of data that is, let's say that a standard is missing. And in general, the concept of SIM as a standard for describing infrastructure is very broad. So it's also sometimes difficult to grasp how it can be implemented. Another question is, how do we map real infrastructure and keep the models up to date, especially when it comes on real time? And finally, how do we ensure, for example, scalability of mapping for mapping all the electricity infrastructure of a country such as the Netherlands? Basically, how do we ensure that we are capable of mapping all the infrastructure from the medium voltage to the low voltage, from the low voltage to the medium voltage to the high voltage in the country, right? And the Netherlands, it is a small country compared, for example, with the size of the power system of countries such as America. So these are not easy questions to answer, but we, TU Delft and Tenet, the operator in the Netherlands, we are working, let's say, to fill this gap. And I want to present to you some ideas and some results that we already have available. So first, I will talk about two concepts that we are currently developing and testing. The first one is called the single source of information, and the second one is adaptation. So the single source of information, let's say as a concept, what it was born out of a result of how can we standardize data across infrastructure data, power system infrastructure data across different teams. And it was born out of a necessity here in the sense that different teams were actually talking about the same infrastructure, but using different ways of describing the infrastructure and often making different decisions because they have actually been used different sets of data, right? So what we saw is that, we need to actually to break these data silos. How do we break different teams working with their own data that describe the infrastructure? So this single source of information concept, which is also used in other industries, is just a concept to let's say, identify a single and unique, it doesn't have to be centralized, data description of DSOs and TSOs, assets, components, and in general, network infrastructure. One way, for example, to implement it, if we think of electricity infrastructure, then we once again can use CGMES as the format selected. And then you see over here that we have, for the electricity infrastructure, we have description of assets such as cables, transformers, all described here, right? And we, of course, need to identify standards for other type of infrastructure. We can think of, for example, the communication infrastructure, how we describe physically where are they located, how they are connected, how they are interconnected as well. The measurement infrastructure as well. And Sync could actually help us to do many of these. So that's what we are investigating. So what's the goal of doing this? Well, if we have a unique and a single way of describing this, then we can think of many tools having an interface towards this unique description of data with the proper data formatting, and then we can ensure that all the different teams are actually making decisions using the right data. So you can think of, for example, teams from system operation, from asset management, from planning, all building on top of the same data infrastructure. Some questions, as I mentioned, are still unresolved. So we talk about other infrastructure, communication, measurements, customers, how this can be modeled, who will be the owner and the maintainer, right? Of course, when it comes to infrastructure data, you also have cybersecurity issues, and then the question if the standard SIM actually fulfills the modeling needs for all the teams, right? So if all teams, for example, the ones working with a different application, Could the CGMS, yes, format actually provide all the parameters, provide all the data that they need to perform their task? The second concept is what is called adaptation. And adaptation basically means that how do we keep parameters of the models updated in real time? And by parameters, we are thinking parameters of the model depending on the type of application. If we are thinking of the power flow, for example, just as the basic application, then we have to think of the topology. We have to think of the ampacity of the cable, temperature. We have to think of resistance, the inductance in general of the cables, operational temperature of cables and transformers. How do we keep parameters so the model still reflects with high accuracy and fidelity the real operation of the system, right? So this adaptation concept, it comes out after, let's say, if we have a model that is operating, there has to be a process, or let's say a moment in which we need to trigger this adaptation process. And this adaptation is, how do we then fine-tune or fit the parameters once again of our model? And we can identify two different types of adaptation issues. One, for example, related to changes in the system configuration and components. You can think of a reconfiguration, and also and the second one, let's say, changes to the parameters itself, or for example, in a more complex unobservable states of the power system. How do we update this? Making use, of course, of data available from the system. So this is indeed a procedure that is complex than just parameter identification, because many of these will actually happen at the same time. So we also need to know which parameter we might need to adapt, and the only, let's say, way that we have to see that we need to sort of trigger this adaptation process is because the accuracy and fidelity is going down. And of course, when we finish this fine-tuning procedure, then we can come back to this continuous operation. Of course, this fine-tuning procedure needs to accept a threshold, let's say, of a residual error in the continuous operation. Now, let me share with you some results, for example, of what we have done together with the operator here in Amsterdam. It is called a work that we did for low voltage network topology correction. So what the case study basically is, how do we recover the topology when there is wrong information about the current, let's say, information that the operator has available about the state of the network in the low voltage system. So what the operators wanted to, let's say, as a challenge to solve, was first identify to which transformers customers are connected, then to which feeders are they connected, and finally, to which phase are they connected. So we have three information that is missing at the same time: the switch state identification, user's feeder connection, so to which transformer, and then to the phase. And we have to do all of them at the same time. Of course, we have some initial information related to the topology of the system. That's what we call it, topology corruption. So what you see over here is a small example in which we have, for example, several switches in which the state of the switch is not known by the operator. So the final topology is not known, but they do have capacity to know the extent of the full topology. So we can, let's say, as a challenge, first identify the switch, then identify the transformers to which customers are connected, and finally the phase in which they are connected. So we develop a routine based on some statistical analysis. We use this statistical metric that is called PCC, Pearson correlation coefficient. And after certain, let's say, procedure that I will not go in detail, let's say, with the statistical analysis, we are able to actually recover the topology and the states of the system. And remember that the challenge here is that we have to do it all at the same time: the phase connection, the feeder connection, and the switch connection of the in the low voltage system. The challenge is, how do we do it in real time? And that's what we are working on right now. Another, let's say, future trend more related to the third question relates to multi-scale approaches. And this comes more of how do we assess decisions in different time scales. And this is what digital twins can actually provide. So coordination of models that are usually operated in a separated way. And now with digital twin, we can actually enable these models to exchange proper data to enhance coordination. So we can think of, for example, trying to, for digital twin to bring together these different, let's say, decision-making processes that are usually run at different time scales. So we can think of voltage control, capacity management, in general, dispatch and planning. So this is what we think of what digital twins can actually deliver. And of course, when we think of bringing together all these different models, there has to be a sort of process for doing some downsampling or upsampling process, because they work with different time resolutions. So data needs to be transferred. And by transferring data, we will also transfer uncertainty between the models, errors, measurements, and of course, dynamics. How do we transfer dynamics between different time scales of models? Of course, some of these dynamics might not be needed to be transferred, but others might need to be transferred indeed. As an example, we can think, for example, of multi-time resolution in general as a scientific challenge. For example, stage synchronization. I will give you an example of one of the case studies that we are working on right now. So, for example, we can think of we want to disrupt the separation of timescales principle in general in power system. And we want to do this by learning how do we transfer data and information from faster to slower models, right? Of course, not needed from all of them. And we have some limitation, of course, computational resources, but then the question is, from the scientific perspective, what do we need to transfer between the models to enhance the decision-making? And one of the case studies, for example, cable ampacity, considering the thermal behavior. So if you think, for example, in general, the time scale of power system, if we go to the very fast, let's say, processes or physical phenomena, then we use different models that could reach up to the Maxwell equations. But if we go to a very slower physical phenomena, then we go to the minutes, hours resolution, and then there are other type of models that could be used. If we are thinking of, for example, the thermal behavior of assets, which are usually described with this partial differential equation, the question is how do we transfer information from different time scales properly to other different time scales in a way that it makes sense and enhance the coordination. So this problem that you see that I describe here is our current one of our current case study, because the Netherlands is right now suffering from congestion, and there are some estimation. The operator have done some testing and operation, and the estimation is that 15% of the capacity of the current infrastructure could be enhanced, and could be, let's say, 15% of extra capacity can be made available if proper modeling and temperature and monitoring is available for the medium voltage infrastructure. So this is one of the cases in which digital twins could provide. Another modeling trend is a new concept, is more theoretical. We call it foundation twins, which is basically, we think of AI, foundation AI models being capable of generalizing over multiple tasks. And you think of, for example, ChatGPT being capable of handling many different topics, right? Although most of the data processing is text, also it could also now process of images, for example. So the question is, how can we make use of foundation AI models to develop the next generation of power system digital twins? And what we are trying to think now is, okay, how can we then put together these models, these foundational models, and this tends to be large models capable of, for example, processing simultaneously different voltage levels, different physical phenomena, different topologies at the same time, without needing to be retrained, the same way that ChatGPT doesn't need to be retrained every time that we talk about a different topic. So what you see here is a theoretical proposal that we are also working on it. And if you are not aware, We have established a European project. This involves a large number of TSOs and DSOs in Europe, which is called AI.grids. And you are welcome to check the work that we are doing. We just started. This is a European effort which aims to develop and understand how foundation AI models could be used in the power system. And we are also testing with multiple case studies. So this is just one proposal of how we, for example, could make use of these foundation models for digital twins. And of course, if you have a little bit of experience with AI, you know that you can use reinforcement learning for decision making, and we can use other different type of AI of machine learning architecture for different purpose. The question is, how do we put everything together to mirroring the operation of the power system? If we think, for example, having a time series foundation model that could process all data from power system in different time resolutions. So we can seamlessly go from milliseconds of data to up to 1 hour resolution data, and simultaneously select the proper simulation, physics-based simulation model with reinforcement learning to make decisions. How this will look like, this is still in development, but I wanted to share it with you. And as I mentioned, multiple scientific challenges are still unaddressed. Another challenge, for example, generative AI, how can we use it? For example, when it comes to uncertainty, we can use generative AI to perform, let's say, estimation of multiple possible realizations of data. And here in this case, my research group has also worked with the operator here to do predictions for different multiple scenarios, considering certain possible realizations of weather. So what we do is that we first do some prediction of weather, and then considering the probability of this prediction of weather, then we can also estimate the possible realization, for example, of the demand. And with this information, we can make use of different type of approaches for handling multiple scenarios simultaneously. You can think of Monte Carlo. So this is also something that is in development. And what you see is that we can foresee or estimate multiple scenarios considering the realization of past events or current states of the system. Finally, I want to share with you a recent national project that is led by Professor Peter Palensky from the head of our group, in which we have actually got a large funding, a national funding, to have the largest RTDS infrastructure in Europe. We are actually in development. This you see here, it is called Utopis. You're also welcome to check what we are doing, but we will deploy the largest RTDS in Europe. If I believe, if I'm not mistaken, it's probably one of the largest in the world. And what we wanted to do, and this is our first, let's say, because of the time, I will go to the next to share with you what are we going to do with the largest RTDS of the world here in the Netherlands. So our ambition is actually, together with TU Eindhoven and TenneT, which is the operator, a national digital twin of the Dutch energy sector. We have just established, as I mentioned, we just got the funding. We are establishing a national facility as a digital twin center for the electricity infrastructure, together with the operator, with the largest RTDS of Europe. And what we wanted to do is to actually model the whole country and develop the models for modeling the whole country using the RTDS infrastructure. Of course, we do not envision a separate tool, but we envision interconnections of tools. So in the RTDS, we will be able to model the power system, but we are also thinking of how can we then couple together models for let's say, more mature models for different type of, from different perspectives of the same infrastructure. So you can think of, for example, thermal models for cables and components, the electricity network models itself, modeling RTDS. How do we model critical users? How do we model the communication infrastructure? And how do we model the market, right? What we wanted to do with this infrastructure is, for example, testing which changes in the market and which changes in regulations would affect the operation of the electricity infrastructure. And this is a signal. What happened in Spain and Portugal is also a signal to see that regulation will have an impact on the physical infrastructure, and now we have the computational infrastructure to test this in the Netherlands. And of course, all the digital backbone that will put all these together. So we are just starting our project. It's called TwinNL. Let me just go quickly. It's a national project with the support of the largest research institutions in the Netherlands and all the operators in the country, with many societal and industrial partners, of course, with support with the government. And if in the case you have heard about TwinEU, I always do this differentiation. TwinNL will deliver the first electricity system digital twin at a national level of a European country, while TwinEU, which is a project that is already being funded and already running, will deliver the interfaces to connect digital twins of the European nations. We want to be the first one to deliver the first model. And of course, throughout this process, there was going to be a lot of learning that is always interesting to see. And with that, I close my presentation. Thank you very much. And if you have any questions, I'm happy to answer.
Yeah, thank you, Pedro. It's a great presentation. So anybody has question, I think please raise your hands. Yeah, Hussein, go ahead.
Oh, sorry, my camera is trying to fix it. Okay, now I should be able to see me. All right, thank you, Pedro. I appreciate it. This was probably one of the very few relative and to the point presentations about digital twin that I've had in the that I've seen in the past maybe few years.
Thank you.
I really appreciate it.
Thank you.
I have a few questions. With respect to how you envision digital twin to play a role, and I think you had a slide, maybe it was a slide number 9. So I understand that, you know, if we want to be faithful to what NASA, you know, presented and defined the digital twin, we want the digital twin to mirror what's happening now in our system. And of course, if we have enough data about the topology or how the load levels or generation mix was in the past or will be in the future, then we can move backward or forward in time. And then especially in real time, because you have the word control there, I as an operator can sit in my in the control room, and I can have a digital twin sitting, you know, beside me, and I can do different scenarios to see what should be my action if this and that happens. And then, you know, whichever scenario, whichever action which is produces the best result, I'm going to do the same in the actual grid. So when you say control, do you mean that the digital twin autonomously control the actual grid, or control in the sense that I just described, you know, basically being played by an operator and provide some insight so the operator can, you know, control the grid?
Yeah, that's an excellent question, Jose. I think that if you ask also to the let's say AI experts, they would say that the future is for AI to autonomously control the electricity infrastructure, so power system. But if you ask that question to the operator, they will say no. It has to be a sort of co-operated. So you can think of the co-pilot, right? So fast decision making, but at the end, the decision has to be approved by an expert from the operators. And this is precisely when what they mentioned to us when we were working together to develop this architecture that I presented here. They say, no, we don't envision this sort of autonomous digital twin with decision-making capability to replace what we have or to replace us. We want for these tools to work alongside us. And that's what we put it precisely here. Okay, then this is something that is outside your, let's say, what you have right now, your control center, but it works together with you.
Okay.
So I would say that is the same answer of as a sort of co-pilot, help making fast decision, but it will not autonomously control the infrastructure. Yes.
Okay, that makes a lot of sense. And my next question was about when you talked about the single source of information, and I was thinking about if there is any, you know, plan forward about kind of harmonizing or merging all of the simulation platforms into one platform. And then I think on the slide number 22, if I'm not wrong, you mentioned something about synchronizing different time scales. I was not sure
Correct.
whether it's about synchronizing the models in different time scales. That's how you want to address that?
Yeah,
Okay.
precisely that, yes. So synchronizing models in different time scale, this is very difficult. So state synchronization is very difficult. We don't envision this single source of information to do that. The single source of information is more of having a standardized way in which all these different tools can actually, so not replacing all tools available, because a particular tool might serve a purpose for a team and not for the other. But what it is happening here, and the operator has shared this with us, is that then asset management is making decisions of a transformer or a cable that doesn't exist anymore because it was already replaced, but they never replaced their database.
Yes, yes.
And that is happening a lot here, and the operators are aware of this. So this is one of the challenges that they have. And what you mentioned of state synchronization is, yes, some models have different time resolutions, but at and some data might be needed to be transferred. How do we do it in a way that we then synchronize the states of the system? That's a challenge.
That definitely helps, but I'm just thinking about the scenario, and this is how I dream about the future. And what I dream, I think, is already in place in some of the other industries. Let's say we have, for protection, we have relay setting protection, we have a different software simulation. For dynamic simulation, we have a different software simulation. Yes, all of them gets the data from that single source of information, so that hopefully will minimize the discrepancies. And we synchronize them as needed through your idea as well. But what happens, or would it be something that, or let me put it this way, I would really love to see that if the protection engineer changes something in the relay setting or adds a relay, etc., I, as a system planning engineer, when I run my dynamic simulation, I see the result of that change in my simulation.
Correct.
And I think in some of the industries, like the automotive industry, etc., they have one simulation platform, but of course the view for the electrical engineer versus the mechanical engineer, they have different view. But whatever change one creates, it will impact the other system that is managed by the other engineer. So
Correct.
I'm just dreaming, if we can get to that point in the energy industry, in the power system industry, that would be very helpful.
I think that we can reach that, but not via sort of all teams or departments using one single tool, but all teams using the same single source of information. So if there is a change in a protection system, this flag needs to go immediately to the single source of information. And because everyone is reading the same source file, that's what we call it, single. So there is only this one, then you immediately should be updated. Your information immediately should be updated. And you should receive the change, for example. That's the general idea.
But if there is a possibility that such information in the other platform can be represented in the other platform, because sometimes we use different platforms because they are tailored for different reasons, they have different representation. So not necessarily everything that is in Aspen one-liner is there in the PSSC. So yeah, that's something. I think there's a gap. I mean, what you're trying to do obviously minimizes the gap for sure. And I know this itself is a lot of work to do. So what I'm dreaming about is very futuristic.
Yeah, indeed. And for example, if you see CGM, yes, it might not have all the parameters that a particular team needs to describe one particular model for one application. So if we are using CGM, yes, and some information is being left out, then that particular team won't be able to use that data. So that's also one of our questions that we have. Yes.
And one last quick question about the RTDS setup. If there's something that you can disclose, what are the maximum number of buses that you want to represent in your RTDS setup? Is it only transmission or transmission and distribution? What is the vision?
The whole transmissions network, yes. The Dutch transmission network, yes.
Okay, very good. Thanks a lot, Pedro. Appreciate it. Back to you, Ravindra.
Yeah, any other questions?
I think there were a couple of questions in the chat.
Yeah, let's just go to question in chat. So I think first question is from Yuan. He says, is the CGMES only for Europe?
I believe it is not only for Europe, because the CGMES is based on SIM. and it's a standard. It's managed by these standards associations. But what I understood, I'm not an expert on the standards, but the CGMES is the one, is sort of a variation that is adopted in Europe. So at least it is the one that we use here. Yes.
Yeah. The next question is from Apur. So he's asking like whether slides would be available afterwards or not.
I could share them with you, Ravindra, yes, and you share them with the participant, yes.
Okay. And then next question is from Junji. So Dr. Vergara, could you please share your insights on foundation model, especially on speed, accuracy, and data privacy?
Yes. So what we aim to do in this European project of AI.grid is to test what would be the added value of this kind of technology for the power system sector. If we want to develop a European foundation model for the European power system, we need data from all the operators. But of course, this is critical data, and national law doesn't allow the operators to share data. So the question is, how do we train a model when we don't have, we cannot collect the data centrally? And this is where, for example, concepts such as federated learning, in which you train the model in a distributed way, will enable to overcome this data privacy. So there are many questions that we are addressing together with all the European partners, but the goal is to have to see what AI can do for power systems. So that's the main objective.
Yeah, next question is from Bisal. From your experience, what do you see as the biggest research challenge in developing digital twins for power system applications?
Okay, yeah, excellent question. So there are different challenges from the engineering challenges, for example, standards, what we were discussing with Hossein, the proper standards for different infrastructure are the standards that we have available, actually covered what the modeling and simulation and team needs from the different teams and departments from the operators. That's more from the engineering side, and there is a lot of challenges there. From the scientific and research part is how do we keep models updated when everything is changing at the same time, right? How do we know which parameter to update? We might be able to get a lot of data, right? If we continue increasing the digitalization pace of the power system, but then which data is needed to properly find the parameters for the models? This is a challenge. State synchronization in the multiple time resolution or time scales, this is also a challenge. Just to name two challenges that we are focusing. And this was very interesting what we did with Aleander, for example, with the operator in Amsterdam, because we have three modeling, or so let's say parameters identifications, the topology, the transformer connection, and the phase of the users. Everything we needed to be identified simultaneously. It's not we have one and then we find the other. And we did it based on data and statistical analysis. So it is possible, but then the question is, how do we do it in real time? How do we do it for different low voltage levels when we have different type of measurement unit, different type of time resolutions as well? This is all research challenge, I would say.
So the next question is from Apur. How distinct do you see the role of digital twin versus decision-making algorithms that are using the twin? For example, using the digital twin insights to make control decision, reinforcement learning to control.
Yes. So what we know as the digital twin is the collection of all these different, let's say, components. So we have the models from one side. We have the decision-making from the other side that could be used, for example, reinforcement learning. Reinforcement learning it learns from interaction with a system from based on data, learns from data or interacting with a system, but you can also learn by interacting with a model of the physical system, right? And in power system, we have that model. So what we call as a digital twin is putting all these, let's say, components and models together and the properly coordination. And if we are properly coordinated and if we manage to do the decision making in real time, we sort of have the models reflect what is happening in the system, and we use the model together with the current data to make decision and then act on the system. this is what we let's see in the digital twin, let's say, being the main application or what they can deliver, let's say.
So, sorry, this is Apurv.
Yes.
Yeah, thank you so far for the presentation. It was really excellent. I just wanted to extend the question. So, do you see the role of the digital twin to be the intelligence layer that tells the state of the grid and what's happening, and then an additional role layer on top of it to use that information to make the decisions on how best to control or keep within the limits? Or do you see you don't see them as distinct layers? You see them as like the digital twin should be able to control and remonitor whether things are back in the limit and maintain that system state, so to speak.
I would say that.
Yeah,
I would say sorry. I would say that it's the first one. So the digital twin should intelligently collect data from the system, estimate the state of the system, use that state to predict what happens, right? What might happen, how the system will evolve, provide suggestions for the operators, or if we are thinking of very short decision-making, let's say horizons, then add upon, of course, with the approval of the operators. But basically processing data in real time, making use of physical models and AI models to support fast decision making. And the flavor that we are giving here to, or we want to give to digital twin, is that this should not happen only in one time scale. This should happen in multiple time scales, because teams are making decisions on different time scales. Decisions about the same infrastructure.
Makes sense. Thanks.
Yeah, I think we are over the time. So before you go, Hussein posted that we have our task force meeting during PS general meeting in Montreal on Tuesday, July 21st, 11 to 11:50 a.m. So if you are attending PS general meeting, please attend our task force meeting there. With that, Pedro, thank you very much for your presentation, and thank you everyone for joining today.
Thank you very much for the invitation.
Thank you, Pedro. By the way, are you going to be in
Thank you.
Montreal?
No, sorry, I cannot travel this time.
Okay, again, we're going to miss you. All right. Enjoy
Thank
your
you very
vacation.
much, Jose.
All right. Thank
You
you,
too.
everyone.
Thank you. Bye-bye.
Take care. Bye.
Bye.